So, we talked about the mechanism of currents across the two junctions in a transistor. Let me recapitulate. We had this transistor in common emitter mode, NPN transistor. I am talking in terms of NPN transistor, but I have repeatedly told that you can use the same language, the same story with PNP transistor. All the arrows are to be inverted and the battery terminals are to be inverted, and electron becomes hole, hole becomes electron in that description. Okay. So, in normal operations, this is important. In normal operations, this base emitter junction, this is forward biased, whereas this collector base, this junction is reverse biased. So, this is an important thing to remember, that it happens like this. And then the biasing is according to this description. This is your emitter, this is your base, this is P, this is N, right? This is N, this is P, and this is N. So, your biasing has to be this way. This P should go to positive, and this emitter is common, and from collector side also you have resistance, and then you have biasing. So, this is now reversed bias. So, what happens because of this forward bias? Lot of electrons are injected from the emitter into the base, because this is heavily doped. So, because of that large concentration, you have this carrier injection is also large, and those things go here. And this reverse bias junction that draws those electrons, because that is a minority carrier here, and reverse bias attracts minority carriers, and so a lot of electrons from this go through this collector circuit, and some small fraction goes through this, and that corresponds to the recombination of holes electrons once these electrons find themselves in this P region. So, this was the mechanism, and under that you understand that IC is less than but close to this IE. The currents are, this is IE, that corresponds to the number of electrons which are being injected from this N side to this P side. So, electrons are going this way, and therefore, the current is this way. Then IC is this is IC, because the electrons are being attracted by this reverse bias, and so electrons are going this way, and so the current is this way, and the electrons which are going in this direction, that constitute this current IB. So, this IC is slightly smaller than IE, and if you compare this IC with this IB, this IC is much larger than IB. So, we normally treat this as the input side and this as the output side. So, you have this input current IB and output current IC, and the current is magnified, current is increased by a large factor. Typically if everything is fine means this junction is forward biased and this junction is reversed bias, and that reverse bias is of sufficient magnitude, and this forward bias is sufficient magnitude. So, if this whole operation that I have told, that only because of the recombination some electrons are going this side, but most of them are going this side, the biasing is such. Okay. In that case, this ratio IC by IB, this ratio, this is fixed. It depends on the concentrations of those impurities, it depends on the geometrical parameters, you know, the base is very thin and all that. So, it depends on all those things, but once those things are there, once the transistor is there, and then the biasing is also proper, right. so that this mechanism does take place, then this IC by IB known as beta, this is constant over a fairly good range. So, this is known as IC as beta, and sometimes it is written beta DC, because we are just taking the ratio of IC and IB. Most of the time people are interested in small changes. So, if there is a small change in IB, what will be the change in IC? So, you can define delta IC over delta IB also, and that will be written as beta AC, but not much difference. Beta DC, beta AC are almost the same, and so if you just call it beta, it is fine. You can also take the ratio of this IC and IE in terms of beta. You know, this IE is IB and plus IC, right. From here you can see Kirchhoff law you can apply here. You have IB going this way and then IC going this way. All this current that IB is here, it has to come from this wire only, and all the current that IC is here must come from this wire only, and so you have this relation. And then if you write this IE is from here if you take this IB as IC divided by beta, so this will be IC divided by beta and plus IC. So, it is IC common 1 plus beta over beta, and hence you have IC over IE. Another useful parameter, what fraction of a emitter current is going through the collector part. So, that is this fraction. So, this fraction is beta over 1 by 1 plus beta, and this is known as alpha. This is written as alpha. So, alpha tells you what fraction of emitter current goes through the collector, whereas beta tells you what is the current ratio between this output collector current and this input base current. Okay. And typically this beta will be something like let us say 20 to 200 or of that type. 50, 100 is quite common, and correspondingly you can see what is alpha, 0.98, 0.99 like that. So, this will be a number close to 1, 0.98, 0.99, 0.995 or 0.985 like that, whereas that will be a big number, 50, 70, 200, 100 like that. So, that is alpha and beta. Now, this zone, this normal operation or the whole this mechanism, when these conditions are met, we say that the transistor is in active region. Okay, we say that transistor is in active region. So, this is the name given, active region. So, in active region your this base emitter junction is properly forward biased, and this collector base junction is properly reversed biased, so that it is ready to receive all those electrons which are coming from the emitter to the base with this fraction, of course, this fraction. So, with that it is ready. If the forward biasing of base emitter junction is not proper, very small biasing or no biasing, zero potential difference, then what happens? If you do not bias, for example, do not bias this PN junction, just leave it open or give it a very small voltage. So, then what will happen? So, you know, this PN junction will not be operating this VI characteristics, you know, VI characteristics. So, you need a small voltage, after that the current starts. So, if this is not sufficiently forward biased, then nothing will operate, no electrons will be injected here, and if no electrons are injected here, no question of any collector current. So, this is also, it is called and it is used. In fact, it looks very trivial to talk, but this is used in certain applications. This is known as cutoff region. Okay. So, cutoff region means no current, IC is 0, and here IC is beta times IB. And there is one more important region, and that is when the base emitter junction is forward biased properly. So, you do have a large number of electrons going into the base, correspondingly there is an IB. But the collector base junction is not sufficiently reversed bias. Okay. If you apply some, say, 5 volts, 10 volts, 8 volts at this collector base junction, good. So, whatever electrons are coming, correspondingly that alpha factor is there. So, that alpha times those are drawn into the collector. But what if the biasing of this collector base junction is very small, is weakened? We apply a small VCC here. This is VCC, remember, this is VCC. So, if there is a current here, you have VCC, there is a drop, voltage drop here. So, finally, the voltage from here to here may be, this voltage may be small, right. If you have a good amount of IB, and suppose beta times IB is IC, so that much current is going from here. So, you do have a potential drop here. So, the potential between this C and E, VCE, that will be VCC here, and minus this, if you call it RL, minus RL times IC. So, at a certain, in certain situations it may so happen that this current IC is large and this drop VCE is small because of this. And if this VCE is small, remember, you also have a drop here. So, your this PN junction, this base collector junction has to be reversed bias. So, it should be more than this voltage, and this voltage is more than this voltage, and therefore, this difference should be this one and plus this reverse bias. So, if this VCE becomes small, then this base collector junction may be hardly reversed bias or zero bias, or in certain conditions may be forward biased. In that case, this mechanism will not work, and then this beta times IB, IC equal to beta times IB, this relation here, this relation, this will not hold, because the collector does not have capability of drawing these many electrons, right. These many electrons it cannot draw, and therefore, we say that it is saturated. The transistor is saturated. The collector efficiency of drawing electrons from the base in the case of NPN transistor, it's saturated, it cannot draw anymore. If you increase IB, proportionately IC will not increase, because the collector is not ready to receive all those electrons, draw all these electrons. So, if that happens, that is known as saturation region. So, there are three important regions in the sense what kind of currents are here, what kind of voltages are here, what is VCC, what is V, this is VBB. So, what is VBB, what resistance is here, what resistance here. So, these things will decide whether we are in active zone, where both the junctions are okay, and then our relation, this relation takes place. And then we have this cutoff region, where the forward biasing of base emitter itself is weak, and therefore, nothing is happening, that is cut off. And then we have this saturation region, where you have current is there, this current is there, is active, the transistor is active, but then the capability is saturated, capability of drawing more electrons here is saturated. In that case, this IC will be smaller than this beta times IB, and if you increase IB, this collector is not ready to respond. So you do have some kind of a constant current after that. So this is these are the regions. So let us now take up what we call transistor characteristics. Characteristics, you know, for p-n junction you draw that IV characteristics like this. Okay, IV characteristics. For p-n junction, just one single p-n junction, if this is I and this is V. What V? Which V? If you have a p-n junction, forward bias, and we apply a V here. So which V I am plotting here? It is the potential difference across the p-n junction, not this V, right? Not the battery voltage that we are applying, not that VCC, VBB, not that, across the junction. So if this is V and this is I in forward bias, this kind of characteristic is shown in the case of p-n junction. For transistor circuit also, here I have two p-n junctions, and therefore two junction voltages and two currents. So there are various combinations possible. In p-n junction there was only just one combination, V and I. So if I have this transistor, and then I have this input side, this output side, then this is base and this is emitter, and you have VBE, the junction potential difference, the voltage across the junction, we write VBE. So VBE if I write here, and then the current IB which is there, this is current IB. So if this is current IB, it will look like this. It will almost look like this. If this junction was not there, of course this is a p-n junction and it should be this characteristic. What is the effect of this collector here? The electrons which are coming, only a small fraction is going. Okay, a small fraction is going. So if this collector was not there, perhaps this would have been in milliamperes. But since the collector is there and it's drawing a large fraction of electrons on that side, so this current will be reduced. So the difference will be that the scale here still can be in microamperes. In a normal p-n junction like this, when we draw forward bias, we write in milliamperes. If I reverse it, reverse bias, then on this side we have in microamperes on this side. The scale on this side we draw in microamperes, this side we draw in milliamperes. But in this case, the shape will be the same, but the values will be different. And this is of course the same, 1, 2, whatever, 1 volt, 2 volt. If it is silicon, you know, 0.6 is the 0.6, 0.7 volt is that barrier, and so it cannot exceed that. So this is the kind of characteristics. This is known as input characteristic. This is known as input characteristics because this whole side is called input side, and IB is the current on the input side, VB is the potential difference on this input side. So this characteristic is known as the input characteristic. You also have output characteristics, and what will be that? Current is IC, and then this VCE, this V and this E. Since we are controlling this potential difference, we are not writing VCB, we are writing VCE. So, if you draw curves of this IC collector current, and here you have VCE. By the way, in this particular case, VCE constant. So, this is constant, and for that you may have to adjust this VCE, because if current is changing, then this drop is changing, and if you want to keep this VCE constant, you have to adjust this VCC here. In the output characteristic, IB is kept constant. For one particular curve, there will be one IB. And to keep this IB same, we are now changing this VCE. So, maybe we will have to readjust this VBB, but not really much. Okay, so let me start with a good amount of this VCE here, and let us say something around 5 volts or 6 volts or like that. So, if this is, let us say, 5 volts. So, I am in the active region, I want to be in the active region, right. Cutoff region, there is no characteristics. So, active region, in active region what will happen? The collector base junction is sufficiently reversed bias, so that it draws that beta times that current IB. So, it is drawing this much of current, let us say, or I have to draw more characteristics. So, let us say this one here, this much, this is the IC, this is the value of IC. What if I make this 5 volt 6 volts? If I increase this biasing here, so that this VCE increases, so it is more reversed bias, what will happen to the current? Since I said that is already in the right region, is not in saturation or like that, so it is drawing maximum number of electrons that it is supposed to do for a given IB. For a given IB, suppose beta times IB should be IC, and it is doing that. That means all the electrons which are being injected here, right, that fraction beta is taken up by the collector, and it is reverse bias, sufficiently reverse bias. If you increase more, nothing will happen, because it is drawing the maximum number of electrons for which this is made. So, just like in reverse bias in this junction, single PN junction also, in the reverse bias the current does not change unless you come to the breakdown as you increase that reverse biasing. Why? Because you have that potential slide, and then the electrons which are here, they are taken up in this side by the electric field. So, whether it is this much or it is this much does not matter, So, the current only depends on how many electrons are available for this drift in accordance with the electric field. So, that decides the current. Similarly, here if I increase the reverse bias, it is already drawing whatever is available, and therefore, not much will change, and this will be almost a flat line on this side. And if you reduce this reverse bias, if reduce this VCC, if you reduce this VCE and you reduce this VCB, see, if this is reduced, then at a certain stage it may not be able to draw beta times IB current, because it may not be able to draw that fraction of electrons into it. The reverse biasing is not strong enough, there are too many electrons, and this small electric field which is there is not able to draw it properly, and that is the saturation region, and in that case the current will drop. So, in that case the current will drop. If VCE is 0, suppose VCE is 0, suppose this is forward bias, fine, it is going here, electrons are being injected here, but suppose this is 0, what will happen? If this is 0, VCE is 0, then VCB will be positive forward biased, because remember this P, this is N and this is P and this is N, and this junction is forward biased. So with respect to this, it is at a positive voltage. So with respect to this, if this is 0, then with respect to base, this is also positive. And so you don't have reverse bias, you have in fact forward bias, and it will not draw electrons from there, and these are lightly doped, they themselves are not going to give sufficient significant current. So this will be almost 0 here. And if this is not 0 but small, if this is not 0 but small, then you will have a very small forward bias to start with. This forward biasing will be decreased. If this potential is same as this potential, VCE is 0, then I said that this is forward biased, because this is forward bias. So from here, these two are at the same potential, so it is more potential than this and also more potential than this. So P in this junction is forward biased. If you slightly increase this VCE, then the forward biasing will be reduced, and at some point 1 volt, 0.2 volt, this will become 0, and after that it will become reverse bias, slightly reverse bias, and then the reverse bias will increase. So what do you expect? The current will be 0 here, and then it will slowly increase, and then when this potential reverse biasing is sufficient, then it will join here. So this will be the kind of characteristic. And what if I increase IB? If I increase IB, if you are in this region, this is the active region where it is flat, this is active region, you have sufficient reverse biasing here, and of course sufficient forward biasing is there. That is why you have this. So if you go for a higher IB, then this side will be all right, since it is at 5 volt, it is ready to accept even more electrons. So that same fraction beta will be maintained, and you will have a current like this. And once again, now you have a larger current. So if it's saturated here, it will saturate slightly shifted here. Okay, because you have more number of electrons, to draw them you need a little more reverse biasing. So this will be shifted here, and it will look like this. It will look like this. If you further increase IB, it will go like this. Okay, so this is the saturation region. This region is saturation region, this is saturation, this region, this is saturation region. This region is saturation region, and this is active region, this is active region, no problem. So this is known as output characteristics. VCE, output side, voltage on output side, and IC, current on output side. So this is known as output characteristics. You can have more characteristics. You can take one parameter from input side, another parameter from output side, and then draw the curve. So if you do that kind of things, you get more characteristics, and collectively we call them transfer characteristics. There may be many combinations. We will perhaps talk one of the transfer characteristics in the next lectures, and then we will go for some applications.